we're going to take a look at what confidence intervals are and how we're going to use them here in this class. So this video is a quick intro into it. So notice so far in a lot of the problems we've been doing, it's mentioned, or it started with something along the lines of suppose the true proportion of something is, or assume the actual mean number of blah blah blah. So a lot of times we're starting our problems with some kind of assumption about what the true value is. In other words, what the true parameter is to describe a population. Um, However, in the real world, we typically don't know the true parameters for the population. Remember, that's what we've also been calling true values. So we don't necessarily know what these things are that describe the population as a whole. So what we do is we're going to end up using confidence intervals to estimate what we think these parameters are, or what we think they could be, or what they think maybe what we think they might be around. So what do? We use data from a sample to estimate those true values. So in fancy terms, using all the statistical terms, we'll use a sample statistic like a p-hat or an x-bar, right? A proportion from a sample or a mean from a sample to estimate a population parameter. So the basic form for all confidence intervals, we're going to take our statistic, which is like that p-hat or that x-bar. We're going to add and subtract a little bit. So this critical value is determined using a level of confidence. Typically that's given in a problem. And then this idea of standard error, which we've just been calling kind of the new standard deviation, right? We've done sigma over square root of n or pq over n because we did a sample. Remember, we always divided back through by the square root of n. So the basic idea is we take a sample mean, x bar, or a sample proportion, p hat, depending on the type of problem, and then we add a little bit, and we subtract a little bit. And depending upon how confident we want to be, the value we add and subtract changes. So how do we figure out the number for these critical values? Because again, if you look back at the formula, we can look at p hat, x bar, that's typically given to us. We calculate the standard deviation with the values given to us. But this critical value right here, right, this one right here, it's it's a new idea to us that we've never seen before. So how do we figure that out? Well, typically it's going to be based on a z distribution. So we could use like an inverse norm function to figure this out, or a very similar distribution, which is called the t-distribution or a t-table. And what we'll do is we'll actually discuss this later in detail as we keep working through this unit. So again, statistic, x bar, p hat, I'm going to add a little bit and subtract a little bit. So here's one of the easiest ways to start considering what is this uh, critical value. So a lot of times you'll see it listed as z star. So think back about our empirical rule. How much of the data was within, or what, z score, might you say, is associated with 95%? Well, using our empirical rule, we know that that's within 2 standard deviations. Now, how could you calculate that if you forget the z-score? Well, what you can do is use the inverse norm function of the remaining area divided by 2. Keeping in mind, again, that that inverse norm function always shades down. And so if you think about it, if this area right here in the middle, right, if this is 95%, that leaves 5% for the 2 tails, which means this would be basically, if you did the inverse norm of 0.025, you're going to get that critical z star value right there. So for 95% confidence, the more accurate result, if you did that in the calculator, is 1.96. We've always used 2 with 95%, and there's where it's coming from. Another common one is 99% confidence. So this time, this number in the middle would be 0.99, which means we need to divide the 1% that's left in the 2 tails by 2, and that's a z star of 2.58. So in other words, if we want to be 99% confident, what we'd end up doing if you go back to your formula is you're basically going to add about 2.5 standard deviations, right? That critical value would be 2.58, and then you'd multiply that by whatever your standard deviation is for your particular problem. But if you want to think about it, it's really like saying, hey, we're doing 2.5 standard deviations to be 99% confident about something, right? If you wanted to be 95% confident, that's a terrible 9, I'm sorry, right? Let's say you want to be 95% confident, the most accepted value with that is basically we're going to say, all right, we're going to take our x bar or our p hat value, and we're going to add or subtract basically about 2 standard deviations, right? So we'll go 2 standard deviations up, we'll go 2 standard deviations down, and we think that the true value is somewhere in between that, right? So these are z-star values probably worth memorizing, and then 90% confidence, that's where now we got 5% on each tail. So to figure out the z-star, you just do inverse norm, 0.10 divided by 2, or just 0.05, because again, that'll find that shaded area down here at the bottom, excuse me, because that's the way inverse norm works, and that's a little over 1.5 standard deviations away. So the idea here, if you notice back, as we get more confident, right, our most confident level is 99% listed here, you go further out. So if you want to think about this, here's another way of kind of looking at it. 70% confidence, you're not going to go as far out. 90% confidence, you're going to want a wider range. One way to kind of think about this in the real world, let's say I wanted to be confident about scores in a football game. Well, if I want to be 99% confident that, you know, one of the teams will score some value of points, I can be more confident by giving you a wider range of scores. If you force me to give you a smaller range of scores, like let's say that, you know, the Indianapolis Colts, I'm 99% sure they'll score between 0 and 100 points. That's a pretty safe bet. But if you ask me, hey, I want you to really narrow that down, maybe I'm more like 75% sure they'll score between 21 and 35, just because you don't want to be as confident with such a smaller range. That's kind of one way to approach this. So we're going to start kind of playing around with this would be confidence intervals for proportions. So the formula for you guys, oh, excuse me, I don't know where my thing just went. So our formula for this, we're going to start with a p-hat, and we're going to add or subtract these z-star values, and then our standard error, but this time it's going to be p-hat, q-hat over n, and I'll explain why in just a second. The most common z-values, again, these are worth jotting down. 1.96 if you want to be 95% confident. 2.58 if you want to be 99% confident. And 1.64. Those are probably worth just remembering along the way. The conditions to use for confidence interval, kind of like we've been doing all unit, there's going to be conditions from here out in this class. The first is always the same. We want to make sure we're from a random sample. This time, we want to make sure our population is greater than 10 times the sample size. Again, very similar. The first two with the confidence intervals, same thing as what we were looking at before. And the next one, in p hat and in q hat, are both greater than or equal to 10. Now, what you should notice all of a sudden is before we used p and q, both in the formula and in the conditions. But now, if you probably, hopefully have noticed that we're using p hat here instead of p. And here's the idea why. This is because, if you think about it, in the real world, go back to the beginning of this video, we don't know the true values. We don't know the population parameters. We only have these samples, and we only have the statistics that we only have the sample proportion, and that's what we have to use to estimate. So that's what we have to use to make sure the condition follows. So quick example for you before you try some on your own. In a random sample of 1,003 U.S. adults, 662 would be happy to spend the rest of their lives in their career. So let's construct a 95% confidence interval to see, well, what do we think the true proportion of adults that are happy with their career is? So what we'd end up doing here, all right, first thing, let's check the conditions. Is it from a random sample? And yes, it is. That was given. Are there more than 10,030 U.S. adults? Yes, there are. And then finally, we need to go ahead and come up with a p-hat, and that's 662 out of 1,003, which is going to be really, really close, I guess, to 62%, a little bit over. It's actually 0.66. So my p-hat of interest here, 0.66. So now we'll go 1,003 times 0.66, and then 1,003 times 0.34. Both of these values are greater than or equal to 10. So my conditions are all met, which means I can move forward with my confidence interval. And so I'm going to go 0.66 plus or minus. So 95%, remember that Z star was 1.96. And then P hat, Q hat over standard sample size. And now it's just a matter of plug and chug. So 0.66 times 0.34 over 1003, take the square root of that. You end up with 0.66 plus or minus 1.96 times 0.015. So we multiply that by 1.96. So we're going 0.66 plus or minus basically 0.03, which means my interval is 0.63 to 0.69. And here's the critical part when you're going to write what this means in context. What you're going to write is you're 95% confident that the true proportion of adults happy with their job is between 0.63 and 0.69. So there's your final answer right there.